streaming and continue with the filter design. So FIR low pass filter design. Do I have my audio on? Yes. So it starts from the setting up the cutoff frequency that actually defines our the sync. So basically that one, we started setting the sync up, which is just basic gives the low pass filter bandwidth. Then we added a window there, for example, a black one window, and based on this frequency response, what we got, that one, we decided actually to okay, its transition bandwidth must be changed. So taking 3 times more points on that window width, you get 1/3 of the transition bandwidth. Okay, so we have all the key parameters on the filter design fixed. So cutoff frequency, stop band attenuation, transition bandwidth. Those 3 things. Okay, so next step would be to actually do some magic and transform this one into, for example, a bandpass filter. So modulate, for example, this one, so that the center frequency would be, for example, 400 Hertz. Does it work? Yes, it does. Okay, let's try that one. So modulate to get bandpass filter around 400 Hertz. So modulation frequency 400, and then we have the modulation is simply cosine, 2 times pi times n times t. N is from -30 to 30, and t is now 1 over fs, so divided by, wait a minute, what do I say here? N times t, ts or f, no, f, no, modulation frequency, yes, divided by sampling rate, yes, that's the way to do it, okay. So that's our modulator, but actually I also multiply this one by 2, since when you modulate it by cosine, you lose half of the signal. Modulator signal. Okay, so oops, wow, what happened? I have one too many of the parentheses. Yes. Okay, so next I'll just multiply everything together and say, okay, this is my bandpass filter design is window dot times that sync, which was the H8, dot times the modulator. So it's the cell-wise product. Okay, modulated windowed sync. There we go. Figure frequency response H8 bandpass. Bandpass. There we go. No, that was the wrong one. Yeah. So started with the low pass filter, which is on the left hand side, and then basically just modulated this one so that the center frequency of the filter is at 400 Hertz. That's the same as the modulation frequency, and we can see we have the same spectral characteristic on both sides of that frequency. So the bandwidth is now 500 hertz. The low pass filter bandwidth was 250, which is also the cutoff rate. Okay, good. But otherwise, these filter properties are actually the same. So the stop band attenuation remains the same. Transition bandwidth remains the same. If you scale the filter properly, then the amplitude response is also the same on the passband. All right. And it's still linear phase response system. How about then the high pass filter from low pass? Low pass, yeah. So we actually have the modulator is -1 to the power of n, or the cosine 2 pi n times Nyquist frequency divided by sampling rate, which means our high pass filter coefficients would be, yeah, again the window, the low pass frequency, low pass filter, the impulse response, and multiply by -1 to power of, what happened? Power of from -30 to 30. I will put some more parentheses here, so just in case. Oh, oops. There we go. So this is actually cosine times n times pi. And again, figure high pass filter. There we go. That's the low pass filter on the left again, and high pass filter. Let me zoom it just about at the same range here, 100, maybe like that. Okay, so it's just the mirror image of the previous. Quite say it makes a lot of sense if you think of this operation, what it actually does. This is the zero plane. You have this first system, zeros are actually something like this. Maybe like that. And when you multiply the transfer function or the system coefficients with -1 to the power of n, you modulate this to here. So it's basically mirror image versus this the z axis. So x becomes -x and so on. So basically it just swaps the axis like that. Or modulates all of these parameters here. So it basically just rotates the whole thing like here. Good. So that's how you make the high pass filter. But okay, on the low pass filter, cutoff frequency is 250. What is the cutoff frequency of the high pass filter? Cutoff frequency 750. Yes, that's the most common mistake on my exercise for high pass filters. To use the cutoff frequency of the high pass filter wrong on when you are designing the low pass filter. Okay. Let's take a quick look here. FIR to match high pass Okay, then noises, voice sample. Okay, with a spectrogram and spectrum, define the filter requirements. Okay, good. So basically, I have given all the hints needed to go with the fourth exercise. I'll just give you one more hint on whiteboard. When you're doing the spectrum analysis of the given sample, the given sample is this voice sample. Yeah. That voice sample, haha. There's some speech actually on speech underneath, but there's so much high frequency noise that you cannot hear it. When you do a spectrum or a spectrogram, you actually see some signal here, then a lot of noise here. How you recognize this is noise? Well, when you take a look at the spectrogram, it just looks like white noise, or well, colored noise in this case. So it's just speckle. On spectrogram, actually, when you go and take a look at the better details of that one, you have some signatures of which look like speech on lower part, and then you have, just noise here. Basically, this is the noise part. This is the information. Now the question is where to put the filter coefficient or filter parameters. What kind of box you need for this design. Your stop and start frequency should be before that point. To get rid of the noise, filter the noise out. It must be that way. Stop and start. FS. Cutoff frequency preferably preserves as much information as possible. So the cutoff frequency should be that way. Okay. If you fix those very close to each other, you know that then you need a lot of points on your calculations to get the transistor bandwidth narrow enough. So it's better to keep those, as far as possible. Still preserve the information and filtering the noise. So basically one more parameter would be how much you must filter in order to reduce the noise level so that you can hear the information. So what do you think? I would say that it must go below this level, the attenuation. And your task there is basically to do the spectral analysis and find out those filter coefficients or filter parameters. Cutoff frequency, stop and start frequency, meaning the transient bandwidth, and the stop and attenuation. So we go back to the defining of the box. Good. So that was all the hints you need in order to do the fourth exercise. And the fourth exercise, let's see. Yeah, deadline is September 30, which is next week, Monday, at 12 o'clock again. Okay, start working.